Today, for the first members seminar, we're very pleased that, that Ben Elias from the University of Oregon has agreed to speak. And the title of his talk today is How to Diagonalize a Functor.
Thanks very much, Mark. I'm very pleased to be here. Thanks for the invitation. Everybody loves eigenvalues. That's maybe a pretty good slogan. Here in particular is a theorem due to, I don't know, linear algebra, which we all learned once upon a time, which says that for an operator on a finite dimensional vector space, having sort of a multiplicity-free minimal polynomial implies that your vector space splits into eigenspaces. Or if you like to choose bases, that V has a basis of eigenvectors, and so F is a matrix where it's diagonal. So maybe this is sort of the diagonalization of F. I don't think there's anybody here who hasn't used this at some point. And I like to think that these are sort of what you want. This is sort of the structural behavior that you're looking for in your vector space. And then this may be a sort of a very easy thing to check. And the interesting part of this theorem is the part that goes, property 1 implies property 2. I mean, the proof is very easy, but I'll remind you of it later, just in case, since I plan to take the method of proof and categorify it. So before I talk about what categorification of this would mean and why you would care, I first want to motivate diagonalization itself in at least one context. I mean, we've already seen many talks that have talked about eigenfunctions and all this stuff. But here's the context that I like diagonalization in. So I'm a representation theorist, so here's an application to representation theory. Exhibit 1. So if A is a semi-simple algebra, this is the kind of algebra that shows up all the time in nature. Like, for instance, if you're looking at representations of a group over the complex numbers, you might care about this semi-simple algebra, the group algebra. Or maybe I'll put in quotes the Lie algebra SL2. If you're interested in representations of SL2, it has the same behavior. So what does an A module look like? So the representation theory of a semi-simple algebra is like really boring chemistry. Normally what you do in representation theory is you try to find all the irreducible representations, the simplest building blocks, the atoms, and then you try to understand how you can glue atoms together to make molecules. But for a semi-simple algebra, molecules are just a bunch of atoms that don't interact. Non-interacting atoms. And the way that you write that mathematically is that if you have an arbitrary representation, it splits as a direct sum over all irreducible representations, so these are the choices of atoms, of a number of copies of that atom. So this appears with some multiplicity. So 5 hydrogens, 2 oxygens, not interacting maybe. And this whole piece right here is the isotypic component of your representation. And this decomposition is completely canonical, and it's called the isotypic decomposition. So what does this have to do with diagonalization? Well, if you pick any central element in this algebra, so anything in the center, then it's going to act diagonalizably on any representation by Schur's lemma. So that's great. And moreover, diagonalizably, and since you have a bunch of commuting operators in the center, you can simultaneously diagonalize them. And so you can look at their mutual eigenspaces. And sort of the simultaneous eigenspace decomposition of the center is the same thing as the isotypic decomposition. So if you have a molecule and you want to split it into its elementary pieces, you can simultaneously diagonalize the center and use this splitting method. That's one of my big motivations for diagonalization. And of course, there's many variants on this story, so I'll just mention very briefly two of them, but I want to get on with it. So, if A is not semi-simple, like for instance, if you take a group algebra of a group in finite characteristic, this is sort of one of the major topics of this special year, then it's still true at least that the center of A acts diagonalizably on any irreducible object. And so that the different eigenvalues of the center, the different eigenvalues of the center will sort of split the irreducibles into different blocks that can interact. You're looking at me quizzically.
Donc le center kan heeft nilpotent element, zo groep algebra.
Sorry, yes, generalizably diagonalized, yes, thank you. Well, wait, hold on. On an irreducible element, Schur's lemma should tell you that.
On an irreducible.
Yes, on an irreducible.
Sorry.
Yes. And so the eigenspace, sort of different eigenvalues will sort of split your chemistry into different kinds of atoms, and only those kind of atoms can interact with each other. And so this sort of splits the category into blocks, and these are sort of a major thing that we've been hearing about in our group seminar for a while. So this is an important concept. And another major thing that happens is that maybe you can diagonalize a large commutative subalgebra, maybe not the center. So if you're familiar at all with the representation theory of the symmetric group, then you often diagonalize this Young-Eustace-Murphy subalgebra. So there's a bunch of things that we use it for in representation theory. You probably use it for something else. But I wanted to use this isotypic decomposition as a prototype because I'm going to show you what happens to the isotypic decomposition after you categorify. And that's going to give you an idea about what it's supposed to mean to categorify that theorem. So this is a talk on categorical linear algebra. And I need to say a few words about what that is, how to motivate what's going on. And it's best to do it in an example because you can get into the weeds very easily. So I think I'm just going to show you an important example of categorical linear algebra and let that sort of stand as its own motivation. So what is a representation of the Lie algebra SL2? This, because of some structural theory, ends up being something very concrete and understandable. You have a vector space V, which is split into a whole bunch of other vector spaces, one for each integer, which are called weight spaces. And you've got a certain amount of structure on this. So if you look at, for any n, the vector space Vn, it has a map, which is usually called E, from Vn to Vn plus 2. And there's also a map from Vn minus 2 to Vn called E. There's a map backwards called F, and these satisfy a relation, namely EF is equal to FE plus n times the identity on Vn. So that if I start here and I go EF minus FE, I'm just multiplying by n for each n. That is sort of what is probably familiar to most of you. Oh, there it is. So now downstairs, this is a two-story exhibit. Or upstairs, I should say. I should show you what a categorical representation of SL2 looks like. So a categorical representation of SL2 would look something like this. You'd have a big category, and I'll remind you what that is in a sec, which is there's a category for each integer. And from between, if two categories differ by 2, there's a functor. goes from here to here, a functor back, and so forth, such that if I start at this category and I apply these functors, I want to get something that looks like this. So functors are something I can compose, and if I'm in the right context, I can also take direct sums. So it makes sense for me to write that E composed with F is isomorphic to F composed with E, and then n times the identity is going to be the identity functor, and the identity functor, and the identity functor n times.
So you have abelian or just additive?
I'll get to what that means in a sec. Sort of this is sort of the natural categorical lift of this, and if n is negative, then this doesn't make sense, but you can bring it to the other side of the equation, and it does. So so if you're not familiar with categories, basically I want you to keep a prototypical example of the category in mind, and this is good enough. So the prototype category is the category of modules over an array. And what a category has is it has certain objects, which in this case are the modules themselves. You should think of these lift what used to be vectors. So if you're in the normal world of linear algebra and you had a vector, you should think of that as being lifted as some R module. And one thing you can do to modules is take the direct sum of two modules to get another module. That is supposed to lift addition. And in all our categories, we're assuming there's a direct sum. And then, so functors are supposed to preserve this. So we're only interested in functors which preserve addition, which is sort of, they're going to become linear transformations. And you can think of this process as sort of remembering sort of just bare bones information about your category. So for instance, you might be looking at modules over a field where this is vector spaces, and you remember just the dimension. You forget most of the structure, and you just remember sort of the skeleton of your category. Now your category has a lot more in it, though. Your category also has morphisms. That is to say, between any two R modules, you might talk about R module maps. And what this corresponds to downstairs is nothing. That is to say, it's a relationship between two vectors. And in linear algebra, we don't really have that kind of concept. Vectors are equal or they're not equal, but there's no relationships between vectors. So this is sort of the extra and the new stuff that we love this stuff. This is sort of the new structure that we have upstairs that we don't have downstairs. So to give you a particular example of this prototype, so here's an example of one of these things. And this example should be enough to give you the flavor of the kind of thing we care about. This example is going to have only 3 non-zero categories. So in the middle, we're going to have something interesting, like modules over the dual numbers. And on the right-hand side, we're just going to have modules over a field. So in other words, vector spaces. And if you're given a module over this ring, you can forget everything except for the vector space structure, also known as restriction, to get a vector space. Conversely, if you're given a vector space, you can sort of double its dimension and induce it up to get a representation of here. And I can do the same thing here. And then you can go home and check that this satisfies the properties that you want it to have. The interesting thing being that if I take a vector space and I induce it and then restrict it, I've doubled its dimension. I've multiplied it by 2, and that's this number here. So this is an example, and to sort of tease what's awesome about this example, this is these 3 rings, K, the dual numbers in K, are actually the cohomology of 0, 2, the cohomology of Ger1, 2, and the cohomology of Ger2, 2. So you might expect that this generalizes, and it does. Okay. I've given you an example, and now I can blather on a little bit. Why would you care about categorical SL2 actions? Well, they're ubiquitous. That's number one. So first off, normal SL2 actions are ubiquitous. They come up from differential operators acting on everything. They come up all over the place in various different aspects of math. Categorical representations of SL2 are actually also ubiquitous. You just may not have seen them in this language. So they act on various moduli spaces of sheaves, or moduli spaces of all sorts of things. So if you think of the Grassmannian as a moduli space, there's also, you can look at, say, coherent sheaves or the cotangent bundles of Grassmannians, and you can use this to construct categorical SL2 actions. There's a recent upgrade of this by Addington and Takahashi, which is pretty fun. There's sort of another ubiquitous source of categorical SL2 actions, and that is representation theory. So another slogan is that representation theory categorifies representation theory. So to give you an example of this, there's sort of a way to take all the categories of representations of all symmetric groups. And glue this into one big categorical action of an affine, I'll just say SL hat, of an affine Lie algebra. So basically, things that you're already interested in, like moduli spaces of sheaves or perhaps representation theory, or perhaps lots of other contexts too, already sort of have maybe invisible, maybe you didn't notice them before, but they already were categorical actions of interesting things, interesting algebras. And so viewing them as categorical actions, it gives you a new perspective on how to study these things you already cared about. So if you can sort of understand abstract properties of categorical representations, you could use that to prove new things about stuff you already cared about. And that's what happened historically. So, for instance, one of the great useful structural properties of representations of SL2, which I already mentioned, is semi-simplicity. Molecules just split into their atoms. Nothing interesting happens. And there's sort of an analog of this if you do it right. So let me now revise the definition of a categorical representation of SL2 to do it right.
Sorry, can you take that as an analog of an SL2 representation in characteristic 0, or?
Yes, you're supposed to think of it as an analog. Well, let's say yes for the moment.
Another question maybe we'll tell later, but equality is a little iffy between functors.
I'm exactly getting to that point. Yes. So, a strong, and this is the correct definition, so I shouldn't really have to say the word strong. A strong categorical representation of SL2 is this data, but more. Because what you have when you categorify is this extra structure of morphisms. And those are invisible in this statement here, except sort of in the sneaky statement of this isomorphism. An isomorphism is realized by an actual map in each direction, and such that the composition is the identity and so forth. And these maps are structure, and if you understand that structure, you can get a much stronger handle on what's going on. So, in addition to knowing this sort of bare bones information, which is sort of just information on the skeleton, it doesn't tell you what's really going on, with certain natural transformations, which I won't go into the details of.
And some compatibility.
And some compatibilities between these things. So I'll state the theorem rather than going into the details, because this will explain the point of this whole digression. I didn't really want to spend that much time talking about categorical representation theory, but I had to, just to give to state this beautiful theorem.
Yeah, and there is only one reasonable definition, or
There's several reasonable definitions, and they're isomorphic. That was a big theorem of Brendan Clustead. So here's a theorem. So the paper that sort of started a lot of this analysis of morphisms and really opened up the field was this paper of Schwang and Ruquier in 2006, where they defined the proper notion of sort of what extra structure should exist to have a good theory of categorical SL2 representations. And if you do that, then if you have an arbitrary SL2 representation, it has a filtration whose subquotients are categorifications of isotypic components. I'll give you an idea, but so this is how you lift this statement of semi-simplicity, this isotypic decomposition, to the next categorical level. And it's great that if you have the right structure here, you do get this, but it's a little more subtle because you only have a filtration instead of a splitting. And that's going to indicate something really interesting that's happening.
To be able to speak of subquotient, you have an abelian category and full Panther.
They proved this exactly in that context. That's right. There's also the triangulated version of this is a semi-orthogonal decomposition. So this now motivates my big question, which is still completely unsolved and open. So this isotypic decomposition is the eigenspace decomposition for the center. And so there's this Casimir operator, which lives in the center of SL2. And its eigenspaces are the isotypic components. Belyakova, Kavanov, and Lauda managed to categorify this Casimir element with some complex of functors. It was a little technical. And so can you use categorical diagonalization to reconstruct Schwang-Ruquier's theorem? Can you reconstruct this filtration using categorical diagonalization? Because morally, it should be something having to do with diagonalization when you're finding isotypic components. This is still completely a wide open problem. But I mention this whole thing because it tells you what you might expect. If I'm going to take that theorem from the beginning of the lecture and try to lift it to something about functors, I need to have a filtration. So you should expect that if you have a functor acting on a category diagonalizably, then maybe you have a filtration by eigenspaces.
But the subquotient are really direct sum of what correspond to irreducibles? Or?
Sorry, say that again?
So isotopic is not clear what it means. Is it direct sum?
Yeah. So I can explain what it is, but I won't do that now. It's a really, really nice theorem. It does everything. Okay, good. We're halfway. So any questions before I move on and actually start talking about, like, I'm going to do now thought experiments to work our way through what categorical diagonalization should be.
No, it's a little strange intuition because if with Casimir you don't see an ordering between the eigenvalues.
Yeah, you got everything that I was going to say already, yeah. So one amazing thing about this filtration is that it sort of comes with a built-in order, right? The highest of all highest weights comes first as the submodule, and then the next one is the next sub, and so forth, on the way down. And so there's some partial order on the eigenvalues, which sort of is built in when you categorify. And that's something that was a new structure which is invisible downstairs. Of course, we know that for absolute representations, there is a nice partial order on the space of weights, but this gives it to you. So now I'm going to sort of switch tacks and try to give an example of what it might mean to do categorical linear algebra. So we're looking at a map from a vector space to itself, and we've decided to lift this to a functor from a category to itself. And an eigenvector would be a sort of a vector m such that fm was equal to lambda m for some scalar. So maybe we're looking for an eigen object would maybe be an object m such that when I apply f to it, I get another object. And, well, maybe that would be isomorphic to some scalar functor times m. So what would a scalar functor be? Well, this would be something like maybe the identity functor. The identity functor should be multiplication by 1. I think we can all believe that. Or maybe the identity plus the identity. That should be multiplication by 2. That's at least one way of doing multiplication by 2. If you're in a graded category, you could have grading shifts. If you're in a triangulated category, you could have homological shifts. There's a bunch of things which are sort of very naturally scalar functors. And you'll see some examples. This is going to be my definition of a weak eigenobject. Because maybe, as we've already seen, you better build in the morphisms if you want to get good theory. But let me give you some examples first. So example 1 is for people who have a little bit of algebraic geometry background, but I'll do something much simpler in a second. So in example 1, V is going to be maybe coherent sheaves on projective space. So something like vector bundles, but you also need to allow complexes of vector bundles. F is going to be the operator of tensoring with a line bundle. And M is going to be a skyscraper sheaf. It's like a vector bundle, but it's only at one point. And it's very straightforward that whenever you take a line bundle around the point where M is defined, it's just a trivial bundle where a tensoring does nothing. So this is isomorphic to M itself. Or perhaps isomorphic to maybe the structure sheaf times N. So this is sort of the monoidal identity functor. O tensor dash is the identity functor. Okay? So a skyscraper sheaf is an eigenvector with eigenvalue 1 for this operator. And I'll be talking about how you diagonalize this. That's going to be what you should think about. So now let me give you a sort of very elementary example. So A is going to be the group algebra of Z mod 2Z. Or maybe I'll write the group algebra of the symmetric group S2. And I'm going to consider A modules. This is actually a toy model for something very important. So you should be motivated by this. I'll explain what it's a toy model in a minute. So we've got some A modules. So one A module we have is the trivial module. So as a Z module, this is just one-dimensional. And x acts by the identity. This is your trivial representation of your group. And this is the monoidal identity. Tensoring as it does nothing. We have the sign representation, which is also one-dimensional, but where x acts by -1. And we have the regular module. A acts on itself. And it's sort of a cute little computation where if you look at A, so if you look at S tensor A, that's just A. So tensoring with S it has A as an eigenvalue. And if you look at A tensor A, you can actually prove that this is isomorphic to A plus A, which you can think of as being 2A, or in other words, the identity functor twice tensored with A. So A is an eigenvector for itself with eigenvalue 2. Okay, so here are some examples of weak eigenobjects. Now, weak eigenobjects are just not good enough. Because, well, in linear algebra, eigenvectors form a subspace. They should be closed under addition, and of course, this definition is closed under taking direct sums. But they should also be closed under subtraction and other sort of operations. And the categorical lift of that would be asking for this eigen category, the set of all weak eigenobjects to be closed under kernels and co-kernels or maybe cones, and that doesn't happen. So that's one reason why this is too weak of a notion, and why if you want to make it work, you need to use some more structure, and this structure is supposed to come from the morphisms. So let's define a morphism. Here is what's new in categorical linear algebra. So suppose that you have a map from your scalar functor to f. I'm going to call this an eigenmap. Some sort of natural transformation of functors or something like that. And an alpha eigenobject is an object M such that when I apply for, a natural transformation is for each object a map like so. And I want this to be an isomorphism. So I've sort of chosen the relationship between this vector fm and this vector lambda m. But in fact, I've chosen this relationship before applying it to an object m. It has to be something sort of global. So this is sort of the relationship between an operator and its eigenvalue. And that's not something you can make sense of in linear algebra. That's sort of a new idea. But the claim is that if you look at the subcategory of alpha eigenobjects, this is closed under kernels and co-kernels and all that sort of thing. And this is sort of the right thing you want to look at.
You take all your functor exact, saying this?
Yeah. So back to example 1. Suppose that f is tensoring with O1. I map alpha from O to O1 is a section. It's some sort of linear function on Pn. And if I look at what happens when I apply alpha to OP, that's really multiplication by the number. I take this function on projective space and I evaluate it at the point. And for this to be isomorphism, we need this to be non-zero. Okay, so OP is an alpha eigenobject if and only if P is not in the hyperplane of things killed by the section. Sorry. Alpha is supposed to be associated with that section S, so alpha and S are the same. So that's sort of a nice example of where the theory actually means something. And in fact, quite a lot of projective algebraic geometry can be rephrased using the language of categorical diagonalization.
If you tensor with O of -1, would you allow yourself tensoring by more ample things?
Sort of backwards eigenmaps, maybe, would be the right theory to approach that, but it wouldn't be forward diagonalizable. Okay? Example 2. So here, S, tensoring with S, had eigenvalue the identity. But there's no maps from the sign representation to the trivial representation. And similarly, this had eigenvalue 2. So if you're looking at maps from the trivial rep to A, there's only a one-dimensional space of maps. So anything like this would have a kernel. So these examples don't work, and these weak eigenobjects are not strong eigenobjects. And this is not going to be an interesting example yet. Okay. Any questions on that? So let me now give you the next big idea. I'm giving you sort of these examples just so I can give you successions of slogans and sort of big ideas in the field to give an idea of what we care about. So, categorical linear algebra, the kind of nonsense I've been doing, is like linear algebra over the natural numbers, which is not something that you do very often. Or perhaps if you're doing graded vectors. So if you have vector spaces, you can sort of take its dimension, and you get a natural number. This is to be viewed as being like a one-dimensional vector space, but we only can see the natural numbers inside it. There's no vector space with dimension -3 or 1/2 or something like that. And by the way, if you want to use graded vector spaces, which is what shows up in most examples, you can take its graded dimension and get a Lorentz polynomial with positive coefficients. So you have a lot more flexibility there, but there's still, you don't have everything in sort of the fraction field in the bigger field. So that's the first point. And the second related point is, moreover, you get a fixed basis. Sort of, your atoms are indivisible and can't be split any further. So, sort of the classes of the atoms are your basis. So the class of the one-dimensional representation, which can't get any bigger, is the number 1. And that's sort of, when you're doing linear algebra with a fixed basis, you don't expect to get an eigenbasis. Eigenvectors are usually weird, crazy linear combinations of your basis with nasty coefficients. And so you don't expect them to be things that come from actual objects. And changes of basis are something that you can think of as being really hard. Maybe I'll keep this definition up for a second. Change of basis is something that's really hard when you're doing categorification. But there's one more important tool that we have. We need to pass to the so-called triangulated setting to expand our scalars. So instead of looking at A modules, we should look at the category of complexes of A modules. But if you take sort of bounded complexes of A modules, or let's say forget the boundedness. If you take complexes of A modules and say mod out by homotopy, you get a sort of nice kind of category, a triangulated category. And now you have a hope of categorifying -3, because a minus sign usually comes from a homological shift. But you also have a hope of categorifying 1/2. So let me show you the kind of thing you can do. You see, over natural numbers, you don't have the number 1/2. But you have the thing that you teach all your kids in calculus, which is that 1/2 is 1 over 1 minus 1, which is by a geometric series that doesn't converge. It's equal to this sum, which doesn't make any sense. But when you categorify this, this could be perfectly sensibly categorified with an infinite complex, where -1 is categorified by sort of a homological shift. And so in this sense, you can take power series of the natural numbers, or power series in this thing, and interpret it sensibly into categorification. So in fact, categorical linear algebra can do a lot of things that linear algebra can't. And for those of us who are going to be studying vertex operator algebras this quarter, I think there's an awful lot of these weird non-convergent or conditionally convergent partial sums in normal order that actually should be appropriately lifted to infinite complexes. This is done by, I can tell you more about that. Okay, so let me fix example 2. And again, I'll motivate this in a minute. But f is going to be the functor of tensoring with not an actual module over the group algebra, but some complex. It's a 3-term complex with this term in homological degree 0. This is multiplication by x minus 1.
A's and z of x, 1x squared minus 1.
Yes, I'll rewrite that. So the kernel of this natural map is this. Okay, this is not obviously motivated right now, but let me show you what happens now. So if I take f tensor A, I already told you that A tensor A was twice A. And A tensor A is twice A, and the identity tensor A is once A. And magically a bunch of stuff cancels in this complex up to homotopy, and you just get A. So this is an example of a weak eigenobject. Again with eigenvalue 1, f tensor A is isomorphic to A. But this time, there is actually a chain map right here from the monodal identity to f. You can check that d squared is this is a chain map. And when you tensor with this, you exactly realize this isomorphism. So A is an alpha eigenobject. And we found something. Okay? All right. So you don't have to follow this exact computation. I want to say you can follow this exact computation. It's a very easy exercise for you to go home and verify what I'm saying. But I'm just trying to give you sort of an example so I can show you what the technology is. Now let me tell you why you care. This A is a toy model for the Hecke category of S2, which is something that's of great interest in geometric representation theory and representation theory in general. And F is the model for a nice central element of this Hecke category. There's a braid group action on this Hecke category, and this is the full twist. And if you knew a little bit about this kind of about this story, you would know that this categorifies, I can't spell it, something with 2 eigenvalues. So we found one of them and we should look for the other. Well, if you have an operator f that has 2 eigenvalues, if you have an operator with 2 eigenvalues, then f minus lambda is a mu eigenvector in the algebra itself, in the algebra of endomorphisms. So how would we categorify? We have lambda, which is this identity right here. We have f, which is this 3-term complex. And how do you categorify a minus sign? So again, another big idea is that categorifying plus signs is easy, but categorifying minus signs requires structure. Again, you need to understand these morphisms. But there's something called the cone of a map in this triangular category. So if I have this complex, I can sort of just glue on that complex at the start to get a 4-term complex. Which is its cone, and this is supposed to categorify f, whatever f categorifies minus to the cool part. So if f minus lambda is my eigenvector, what is its eigenvalue? So if I take f tends to the cone, I'll skip this computation, you just get the cone with a homological shift. It gets moved to the right a little bit. And so you have the identity with a homological shift. So here's homological degree 0. You've got f. And once again, you've got a chain map. And it turns out that this cone alpha is a beta eigenobject. So we found two eigenmaps, two eigenvalues, and two eigenobjects. And one of them was a complex. And as I said, again, you're not expecting to get a nice eigenbasis if you just look at your original category. Eigenbases have weird coefficients. And so, in fact, you have to look at something like, some four-term complex before you get an eigenvector. And in fact, this in the Grosvenor group, this is 0. So everything cancels out. So in fact, it's kind of invisible downstairs. Okay. So finally, you can then confirm that cone of alpha tensor cone of beta is 0. And this is what categorifies f minus lambda, f minus mu is 0. So in example 1, which is coherent chains on projective space, if you chose S0, S1, SR, a basis of sections of O1, then the tensor product of the cone of O of 1 is the causal complex, which resolves the place where all the sections simultaneously vanish. And in projective space, that's the empty set. So this is actually the 0 sheet. And this is supposed to be, you're thinking of as categorifying sort of f minus lambda 0, f minus lambda r. Any questions before I state something resembling a punchline?
When you work in a triangulated setting, there are also always high or homotopies lurking around. So can you manage them?
Right. And the answer is that's tricky, but yes. Absolutely, that's very much a cause for concern. So one thing that's true in linear algebra is that these operators, f minus lambda 0 and f minus lambda 1, all commute with each other. The polynomial ring in f is commutative. But the polynomial ring in this functor, capital F, is not commutative. So we need to impose some sort of commutivity conditions on these maps for our theory to work. Okay, so I promised you I would prove something in linear algebra for you. So let me go back to this original theorem. So if Q is the polynomial x minus lambda 0 up to x minus lambda r, and if Q of f is 0, then this is supposed to imply that V splits into its eigenspaces. The proof that you might have taught your students once upon a time in undergraduate algebra, or sorry, maybe in graduate algebra, is using the Chinese remainder theorem to argue that fx mod q sort of is isomorphic as a ring to a product of these fx modulo of these prime factors. And you can use sort of the element 1, 0, 0, 0, 0, 0 to project to the lambda I eigenspace. But there's a sort of much more explicit proof due to, I don't know, I'll say Lagrange. I mean, I'm sure it was, I don't know if it's fair to attribute anything in these classical linear algebra stuff, but there's something called Lagrange Interpolation. Which explicitly constructs projection to the ith eigenspace as a polynomial in X, in the operator F. So you set Pi to be the product of all the other eigenvalues of F minus lambda j over lambda I minus lambda j. And this is supposed to project to the ith eigenspace. So because of the numerator, it kills all the other eigenspaces, as you want it to, and then it gets renormalized by the denominator to fix the eigenspace. So the real question now is how to categorify this. I'm going to show you how to do it in this example. So in this only two eigenvalue case, so the projection to the eigenspace for lambda is, this has a single term. And you can rewrite this as a power series. So if you factor out a copy of lambda inverse, then the denominator is a geometric series. And so you get some infinite power series. Now, I'm going to take this infinite power series and write out what you would do naively. So if alpha mu, if it was this thing for which the cone of alpha mu was this 4-term complex, again, you don't need to remember the details anymore. Well, this is supposed to be categorified by this cone. And so we need to now have infinitely many of these things with shifts. If you work out the shift, it looks like this. And I'm supposed to take the direct sum of everything in each column to get what happens in each on 1 plus 3. So I've got infinitely many copies of this, and that is a categorification of this. But this would be a very boring complex unless I was clever and I used, so this was the map alpha mu, the map I was calling alpha. Here's beta, the other eigenmap. And I can use this to link them all together into a big infinite complex, which is interesting. These identity terms cancel out in the homotopy category, and this becomes this infinite complex. Like so. And you could do something similar to construct the other complex. P, U. So this is just, I wanted to give a picture of this as some sort of, take something in linear algebra and come up with a very clever way. This is what my co-author Matt Hogenkamp is very good at doing. Come up with a very clever way of finding some homological algebra to mimic what's happening in algebra. And then you have to prove that it works. But that's something we did. So I'll say the theorem and I'll shut up. And so the theorem, which is exactly going to go, I'll write it over here. So the theorem is that under some technical hypotheses, which of course exist, if you have a bunch of maps, alpha I, from a bunch of scalar functors to a functor f, and I'm assuming that f is invertible, because otherwise you don't know how to crank this machine. And the tensor product of these cones is 0, then you can construct these infinite complexes built up out of copies of f and all these various different shifts, which project to the lambda I eigen category. So the space of eigenobjects for alpha I, and that this actually equips your category with a filtration by eigencategories. And finally, there's applications of this, so it can apply to the full twist on n strands living inside the Eigen category. And so using this, you can do a lot of the representation theory of symmetric group lifted to the next level. Thank you very much.
Thank you very much. Are there any questions?
The theorems are the eigenvalue commuting in some sense?
Yes, so there's a whole lot that's hidden in here. One of the big ones is a commutativity. And another big one is some sort of convergence of the power series. And so the convergence of the power series sort of says that you're choosing some topology where this infinite sum makes sense in the homotopy category. In particular, like these things have to have distinct homological shifts, which actually makes it rather restrictive.
So in the projected case, this projection is restrictively open and pushed back forward.
Yes, it seems like that, except it's a little bit trickier. So this theorem actually doesn't apply in that case directly because of the convergence issue. All these eigenvalues are the same, and so you don't expect this to converge at all. But if you work equivariantly, C-star equivariantly, or for a regular element of the torus, then you can actually distinguish between all these different shifts. And then it will work roughly like that, yeah. So that stuff is actually, that exact example is written up very carefully in this paper of Gorski, Niguts, Rasmussen. I don't want to mess it up.
When you expand 1 over 1 minus x, there are often two ways of doing it, depending. Is there something analog happening?
Right, so if you tried to use the exact same expansion for p mu, you'd end up with like an infinite sum of lambda over mu. And it's very unlikely that both of these things converge. So in other, if x is absolute value less than 1, then 1 over x is absolute value bigger than 1. If you think about it this way, when I did this version, I got sort of an infinite complex that was bounded above. And if I did it naively for the other one, I get an infinite complex bounded below. You don't want to tensor those things together. You want to stick to, say, bounded above complexes. And so then you have to expand this in the other topology to get the other power series.
I get sort of confused about what equals 0 means.
Equals 0 in this case means in the homotopy category. So it's
I know, that's what's confusing. You don't keep track in any way?
Do we keep track of the homotopies that make them 0?
That
right.
seems like it's quite relevant when you're constructing.
Absolutely, I agree. So there is another technical hypothesis, but it's actually not so bad. So there's some sort of hypothesis which is very related to the commutativity hypothesis, where if you assert that, then you don't actually need to keep track of anything higher. So it's just the vanishing of some particular class in some particular. I don't want to state it aloud, but you actually don't need to worry about this. It turns out you don't need to.
But that surely isn't true, generally speaking, is it?
Yeah, right. I mean, I do not know.
I mean, there should be higher homotopies all the way somehow.
Oh yeah, of course. So basically, it's really not that bad a condition. For all the examples we have in mind, things like the full twist, there's some sort of really nice parity vanishing, which makes all these higher homological obstructions vanish immediately. So We weren't focused so much on dealing with the worst possible generalization of this.
Can I ask a more philosophical question?
Yes.
So assume I come from the categorification side. I have a categorification where I categorify projectors like you have. Can you say anything about the spectrum, to the eigenvalues which occurred from the category?
Right. So it's a very good question. So what is the right notion of a spectrum? Already you can see some of the thorny issues. So being an eigenmap is an open condition. It says that something is an isomorphism, which is to say it's non-zero when applied to a given object, for instance. So if you looked at that example in coherent sheaves, if you're asking for which eigenmaps is OP, an eigenobject, well, any section which doesn't vanish at that point, and that's an open condition. So if you have sort of overlapping eigenobjects, then you start having this situation where you've got sort of, it's not clear how you should sort of split this category into various different eigenspaces, and there may be more than one way to do it. Is it rigid or is it not rigid? It's a very complicated question in general. In specific examples like this one, it ends up being quite rigid, and you can really say that this is the spectrum. But as evidenced by algebraic geometry, like it very much is a complicated question.
So can you say it for n equals to 2, for instance?
For n equals 2, I just gave you the spectrum. So the two eigenmaps that I wrote down are the only eigenmaps.
Ah, these are the only one, okay.
Yeah.
Okay, yes.
Up to scalar, right? So again, they're
okay.
up to invertible scalar.
Okay. Thanks.
Are there any other questions?
So you mentioned the categorified Casimir operator.
Mm-hmm.
Are there other examples of operators, besides sort of these Juicy-Murphy's operators, or that might be interesting to diagonalize?
Right. And aside from line bundles and coherent sheaves, and other sort of vector bundles and coherent sheaves. So the vector bundles and coherent sheaves is in quite a few examples, right? And what Gorski and Rasmussen do is they sort of use this general framework of diagonalization to talk about what it means to be a category living over coherent sheaves on projective space, or living over coherent sheaves on other quasi-projective varieties. So that's sort of a very sort of powerful and general example, very general example. But sort of as far coming from the categorical representation theory perspective, we've got categorifications of only so many things. We've got Lie algebras, and if we can't do the Casimir, you shouldn't expect to do too much more there. We've got Heck algebras, and then we've got uses Murphy's. That's sort of in the bag. That's good. Although other Coxeter groups are still open. And we've got sort of Heisenberg algebras, and that's sort of. I'm not sure if there's so much to say there, because once you diagonalize there, you're actually switching into your framework into the quantum group setting. So I'm not sure if there's any other thing I can really point to.